Hello everyone, we are here with another section of the CA320 Computability and Complexity course. This week we want to talk about the functional programming and Haskell. So we have two major programming paradigms, the imperative programming and functional programming. In imperative programming, we have instruction, and this instruction used to change the state of the machine. For example, if you have a variable x, that instruction can change the value of x inside the memory, and these instructions are evaluated sequentially after each other. So for example, if you want to calculate the summation of 10 numbers, number 1 to 10, so that could be a very typical lines of code in imperative programming paradigm. So you have you initialize a counter like total, and then you go inside the loop and you add the things, change the value of total to a new value, and come back and continue until you reach to the end of the loop. But in functional programming, actually our expression are used to give the program a value. For example, we are not interested how f of g of x is generated, just we are interested in the value of f. If we give an input, we are interested in the output. And so order of evaluation is given by dependencies on expressions. So for example, if you want to calculate the summation of 1 to 10, we don't need to list all of the instructions sequentially to calculate that. Just you can say sum of 1 to 10. So that's the main difference of imperative and functional programming languages. So let's look at some properties of functional programming languages. It allows the programming to take a high level view of what is to be computed rather than how. So we are interested on what is going to be calculated. We focus on the problem instead of focusing on the solution. Okay, so what is going to be computed rather than the how. So programs are built out of the expressions whose meanings are values. There is no notation of the state, no variable or assignment, etc. So there is no sequencing, and functions do not have any side effect. That's a very interesting properties of the functional programming, which they don't have side effects. For example, if we have a variable like x, we don't change the value of that variable x inside the memory by going to different things we are doing in the programming. Okay, we will look at that a little bit more in details later in the coming slides. Okay, so when we remove updatable variable from a programming language, there are a few other casualties. In particular, the iterative constructs like while and for loop no longer make sense, since we cannot change the variable that might appear. So since we cannot change the content of a variable, so it doesn't make sense to have while and for loops. Hence, the only way to implement iteration is a functional programming. So we don't have while and for. So for iteration stuffs in functional programming, we should use the recursive functions. So for example, if you want to calculate the factorial of n, it would be if n is equal to 0, then if n is equal n factorial of n, if n is equal to then 1, otherwise it is like that. So you'll get familiar with this style of programming in functional programming. So you say if the n is input, then if that input value is 0, the output is 1, otherwise the output would be something like that. This compares, you can compare it with what exactly we do in the imperative languages and imperative programming. Okay, so when we use an expression, we are only interested in its value, and for function in its return value. So nothing else can have any effect on the rest of the program. And so this property is known as referential transparency. Okay, so that's something we are facing with in functional programming. Basically, if we take an expression anywhere in a program and replace it with another expression that gives the same value, we will not have any change the overall result of the program. So that's exactly what we talk about, the side effect, which we don't have in the functional programming. I mean, if you have a variable or something like that, no matter in which program you use it. Since it is fixed, the value of that variable, you never will face any changes in the results, because all the time it is fixed and we are not going to change the result, the value of the variables. Okay, so in the first glance it looks like a little bit impractical, the functional programming, but we will show that there are lots of interesting things we can do with the functional programming. And imperative programming languages, they have arisen as an abstraction of hardware. So we have had hardware, and based on the hardware concepts we try to design the languages, imperative languages. Okay, so in other words, we have started from the machine, and then those languages are kind of the machine code. So languages like assembly or C, Java, etc., something like that. Perhaps this is a wrong approach, and we should approach the task by modeling the problem rather than the solution. So in the imperative languages, imperative programming languages, we have focused on the solution. We have started from the machine. We have designed machine codes, and then those languages have been formed. But now in the functional programming, we focus on the problem, how to solve the problem, not focusing on the solution. Think about that a little bit. It is an interesting idea to realize what is the difference between these two guys. Focusing on the problem rather than focusing on the solution, right? So that's the advantages. These things, they don't make sense in the imperative languages at all. And like we said, these equalities are hold for functional languages. In functional programming languages it makes sense, but not in the imperative languages. This makes functional programming easier to reason about. So it is much easier to reason about the functional programming. It also makes functional programming easier to run concurrently, and that's one of the main advantages of the functional programming. Writing programs in a functional style also promotes good programming practice. So that's another good reason why it is recommended for the beginners and for the people who want to improve their capability in programming to focus on functional programming, because that's a good programming practice. Functional programming. Functional programming is not without its deficiencies. Definitely, there are some cons. It's not all pros. There is nothing all pros in the world. Everything that they have pros and cons. Some things are harder to fit in the purely functional programming. Okay, we will face it that later. So functional languages also correspond less closely to current hardware. Like we said, imperative languages, they have started from the hardware and hardware limitation, and then machine code, and then languages. So the functional languages, functional programming languages, are from the other way around. So that means it would be sometimes less closely to the current hardware. So they can be less efficient in this sense, and it can be hard to reason about their time and space usage. Anyway, so if you can see some example of functional programming languages in the world. Lots of functional languages programming you can see nowadays are available in the world. Google, Ericsson, Facebook, and so on, they are using their own languages. For example, Facebook, one of the interesting things that Facebook has done with the programming languages, it has been the spam killing inside the Facebook using the programming languages. You can look at that and see how they have done this and what has been the algorithm. And so these are some of the languages. Fhash, Erlang, and Scala are attracting a lot of interest from developers. Features from functional languages are also appearing in other languages. So they have understood they can use this kind of capability of functional languages and bring them into other imperative languages. For example, these are some kind of the examples that we are facing with in this area. Okay, Haskell is one of these programming languages, which was designed by Simon Peyton Jones, and the language was called Haskell because of the name of the guy. Okay, Haskell B. Curry. In the beginning they wanted to name the language as Curry, but later they realized it's better to go for the first name than the last name. Okay, so that's the name of the language because of the name of the guy who used to work on Lambda calculus, which is very related to the functional programming basis. Haskell is almost a purely functional language with no side effects, and referential transparency with the expectation of input-output. That's a very lazy programming languages. Later we will see what does it mean, the lazy programming languages. And that's a statistically typed, statically typed. What does it mean? Type language. So at the compile time, we know the type of each expression. That's really restricted languages in this sense. Type inference system is very interesting thing in the Haskell languages. That means tries to work out the type of an expression if it has not been. If you declare the type of the variable and the thing and the function you are using inside the Haskell, fair enough. But even no matter if you have defined, declared, or if you have not declared already, what is happened is the system, the Haskell itself, tries to inference the type of the thing you have defined to see if it is correct or not. So as you can see, that's really restricted language in terms of the type of the things you are using in that, and that's the reason why there is less bug. In other languages, you have some other languages which you don't have any restriction on these things, so that means there are lots of more bugs. But in here, like I said, less bug we are facing because of the restriction. We will see that later. Okay, so what is the compiler of the Haskell languages? That's GHC, is a leading implementation of Haskell and comprises a compiler and interpreter, both of them. The attractive nature of the interpreter make it well suited for teaching and prototyping. So if you go to this website, you can find it for different platforms, for Mac OS, for Windows and Linux, and you can install it. And then after you install it, the GHCI, by typing GHCI in command line, easily you can run the compiler and you'll see this message in here. So the prompt, GHCI prompt, which we are talking about, is where actually that means the interpreter is ready to evaluate an expression for you. For example, you can work very similar to a calculator in here. You can do different things in here. So there are lots of functions, built-in functions in GHC, such as plus, multiplication, and so on, that you can use it in the interpreter and even in your functions and your program, etc. So there is a package which is called load. When you run the GHCI, automatically this guy is loaded by default, but you can change the default and you can say if it is loaded or not loaded, or even partially loaded and something like that. But that's something, when you load it, you have lots of this built-in operation available inside that. Okay, let's bring it back into here. So as well as the functions in Perl, you can also define your function yourself. So for doing that, you can define scripts, which this script should have the extension of that HAS. There is no restriction on that. It could be any kind of restriction, even the dot text, but it's better to stick on the regulation. It's not mandatory, but it's useful for the identification purpose to use dot extension for your Haskell scripts. When developing a Haskell script, it's useful to keep two windows open. Okay, so in one window you can write your code inside the script, and inside the other window you can load the script and execute it to see what happens. Okay, there are some commands you can use with Haskell. For example, .load, the name of the script, loads the script for you, or it could be colon L, or reload. You can reload the script again after some changes you have applied to it. It could be $R, and so on. Colon question mark will gives you all the commands you will have access, and also quit is something you can use for quitting from GHCL. So that's the whole story of the function inside the Haskell. You will have two inputs, multiple inputs, let's say, and you will have only single output. That's very important. You will have only single output, and the result would be we will often use the term result for the Haskell functions. We will often use the term result for the output. We can use it. And also the input values are called arguments or parameters. A simple example of that is the add function, which takes 2 inputs and generates 1 output for us. Okay. The type, what is the type? We say that's really restrictive language in terms of the type. Okay, what is the type in Haskell? The type is a collection of values such as a number, images, grouped together, because although they have different two, yeah, you know what does it mean when we talk about the numbers in terms of the type. Even that's the case in other languages. That means any kind of the numbers could be inside the numbers, could be any I mean small number, large number, or even integer or floating point or double or something like that. So functions operates over particular type. For example, a function to scale an image will take 2 arguments, one of the type image and the other one integer. Okay. The syntax in Haskell we use to declare the type of a variable is like that. This double colon is for declaration of the thing, the name of the variable and the type. Double colon means is of type. This variable is of type this type. Answer is of type integer. Okay. So equal is used to make definition in Haskell. So in here we have defined the variable and declared the type, and then in the next line we have defined that variable with 40. Okay. Answer is of type integer, and then answer is equal to 40. For example, in this one, we can declare in this way also. So we can say size of is type integer, and then size is equal 12 plus 13. Okay. And we can even do something like that. Imagine we define black horse is type of image type, and then black horse is equal to invert color the image horse. We have an image horse. We use this function to convert it to the image type of image and then put it inside the black horse variable. Okay, so that's the definition of the variable, and that's the declaration of the variable, and that's the definition of that. Okay, this basic syntax for defining the function. How we start defining a function in Haskell, that's very similar. First of all, we define the type, and then we define the body of the function. Very similar to other languages, a little bit different in here, but the concept kind of is the same. So for example, we say the function square is from type of integer to integer. That means the input is integer and the result or output is integer too. And then later we define the function. We say function square takes the input x and generate the output x times x. It doesn't mean assignment. You assign this guy to this guy. No. The syntax means in the left hand side of the equal sign is the input, and in the right hand side of the equal sign is how the output is calculated from the input. So that's the definition of function square. Very simple function. So that's another example. Look at that. So all equal is a function of type integer, 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 and then Boolean. What does it mean? It means since we have only one output, so that means this guy is output and the rest are input. So these are inputs. We have 3 different inputs of integer, and then we will generate one output of Boolean. So n, m, p are the input, and then the output would be if n is equal to m and m is equal to p. Okay, so we describe everything in here. We don't need to go through that. We have another concept in Haskell which is called guards. Guards or tests in Haskell are kind of very similar to switch case, or very similar to if else, something like that. So are Boolean expressions, very similar to if else, because they are Boolean expression, right? Okay, so we'll say syntax is something like that. We have the syntax. Let's go to an example and understand what's the syntax. You say I have a function of maxi, which is type of integer, integer, and integer, 2 integer input and 1 integer output. And then I would say, you remember, we used to say the name of the function, the input, and then equal, and then how the output is calculated. But since we have multiple cases in here, we use this syntax. You say input, and then this vertical line, the output would be n. If n is greater than or equal m, the output would be n. Otherwise, it would be m. Okay. reading of the, if n is greater than equal m, then return n, otherwise return m. Okay, so it could be even multiple of that. It could be condition 1, condition 2, and so on, and then the last one would be otherwise, which is very similar to else if, and the last one, you know, that's a default one kind of. So for example, in this example, max is to return the maximum is 2 integer arguments. So function max is of type integer, integer, and the output will be integer. If you take input n and m, if n is greater than m, then output is n. If they are equal, also the output is n. We could mix them together. We could say n greater than or equal m, then the output would be n, but we have separated them here into different lines, and otherwise it is n. Very similar. So see, very simple syntax, just you need to learn the syntax. Okay, if you want to comment a line in Haskell, double dash is the syntax we use for it. If you want to comment multiple line, so we use this syntax for that. We start with this curly brace and line dash, and then another dash and close curly brace to finish the multiple line commenting, right? So we have error function in Haskell, very similar to other languages. That's a built-in function which generates for us error messages. We can generate error message ourselves. We can call the error message and then the text of the error message we are facing within here. Okay, so in this function, for example, we take the values ABC. That's not the complete definition of this function specifically, just we want to focus on the error message. Okay, and then function will halt and give the error message if the error happens inside the these guys. Functions and argument identifier must begin with the lowercase. See, lowercase, 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 lowercase. It is okay to use underline. It is okay to use prime in variables and function naming. For the list, we used to use the suffix s, for example, xs, ns, xss, and so on. You will see that what does it mean later. You cannot that's very common. You cannot use the name which already have been used in built-in functions. Okay, and also there are some reserved words very similar to other languages. You cannot use these words also. Okay, in terms of the type inference, like I said, you need to declare the type of the variable and function you are working with. It's not mandatory, but in the compile time anyway, Haskell inference the type of the things you are using to see if something is to see if everything is fine or something is wrong. Okay, values can be of basic type such as integer, boolean, and these are the different types we are facing. You can have the integer, you can have float, a boolean, character, and so on. Okay, we can have the compound types also, tuples, list, string, and functions. So function is a type also. We need to have type for function. We need to have type for, we have type of a string, which is multiple of characters. We have lists, very similar to Python list we had here. And we have tuple, again, very similar to Python tuple definition. Okay. Numbers in Haskell can be integer, int, or integer. Int is limited to smaller size of the range. You can select that 2 power minus 63 to 2 power 63, but integer is anything, any large number you can have. And for float, you can use different kind of the notations. You can use like this, you can use like this, or like this. And you have infix operators. Infix operators are operators which comes between different variables and numbers. It could be summation and all these guys, as you can see here. So that's example. So that's infix operator has appeared in here. And for example, the module is another infix which we have it. So division, which could be something we use in here, or it could be even be used as the infix, very similar to this guy. So it could be 5 single quote, 5 single quote, div single quote, and 2, or it could be like that. And we have two kind of division in here, as you can see. In division in here we have the integer division. See, the result is 2, but in here we have the floating point division. You have the exact number in here. Like I said, for the infix operators, you need to use this double single quote in the operator inside that. Actually, the booleans we have, which is true and false, we have some operators like this guy for logical and logical or and not logical for logical negation. Okay, so also we can use these operators very similar to other languages. And yeah, that's the whole story. True is true, false and true is true, or sorry, you know, you're familiar with these things. I don't need to go through these things, all of them. So value of type character are individual Unicode characters. Okay, so literal characters are written with a single quotes. We can have single literal characters in here. So, and some special characters are represented as below. We have these characters similar to other languages. We have special characters, you cannot use them. For example, tab, this guy is used for tab, for the next line, and so on. Okay, so if you want to use backslash, you need to use another backslash also to protect it, and so on. So literal strings are written in double quotes. For example, that's a literal string instead of literal character. We had the literal character, you remember, in single quotes, and literal strings can be written in double quotes like this, and also these guys. So when GHCI interprets this string, for example, take this guy as a new line. So when you want to print it, so if you put it in front of the interpreter, it exactly the string will be printed in here, and this guy is not considered as the new line stuff. But if you want to use the put string to print it on your terminal, then this guy is considered as the new line in here, and you will go to the new line. So that's the difference. If you put it in here in front of the interpreter, you just print the whole string. But if you use a function put string, you will print the result, and then \n would be as kind of a notation for going to the new line. So like I said, we have lots of built-in function. You can see in here, very similar to other languages, absolute value or rounding a number or a square, stuff like that. You are familiar with that. I don't want to go through that. Where clauses. Okay, where clauses allow local definitions. We want, you know, what does it mean, the local definition? That means defining something inside a function. That's a local definition. If you want to define something inside this guy, you can use where clause in here. How? Let's say I have a function point, that's the declaration first. I have a function types points, is type of integer, integer, and integer, inputs and output, and then I define. I would say points for against, they are the input values, integer and integer. If diff is greater than 0, that's a guard, right? In here, that's a guard. If diff is greater than 0, equal to 3, output is 3, and so on. But you say, I don't see any diff in here. There is no diff in definition for against and so on, until I get to here, to the last line, which says where in all these stories diff is equal to 4 minus against. So if you take 4 and against, and then diff would be the subtraction of both of them, and then if the subtraction is greater than 0, then output is 3, equal to 0, output is 1, and 0. Okay, it is important to remember that the definition diff only applies inside the definition of points. This is why it is called the local definition. Okay, what is the associativity in Haskell? Some operators are associative. For example, 4 plus 5 is equal to 5 plus 4. Okay, there are many non-associative operators. However, for example, look at that. What does it mean? Should I subtract 4 minus 2 first and then the result minus 1, or should I subtract 2 minus 1 and then subtract that from 4? So that's the first one. 4 minus 2 is 3, 2 minus 1 is 1. But in this case, 2 minus 1 is 1, 4 minus 1 is 3. So this guy, if I use like that, it is called left associative. And if I do like that, it would be right associative. Okay, some operators are right associative and some of them are left associative. For example, look at this guy. This guy is right associative. So by doing that, it means I will do first of all 3 power 2, which is 9, and then 2 power 3, which is 5, 12. Okay, these guys are left associated, so you can find in different cheat sheets what operators are right associatives and what operators are left associative. Function application in Haskell, they are treated as the higher priority, and so they are left associated. So functions in Haskell, they are left associated. For example, if I say add 3 for this infix operator and then 5, what will happen? Clearly add is a left associative, so it would be first of all add 3 to 4, which is 7, and then times by 5, which is 35. Add 3, what about this one? What about this one? That's clearly you have, so which are this one would happen for this guy? For this guy, definitely the first one would happen, because that's a function, and function is left associative. That means you will start from the left. Okay. Polymorphic function, that's very interesting characters of the functions in here we want to talk about. So we define the function like this. This function is type of integer, and Boolean, and then the input and then the output. Ordinarily, you define the function given the argument types in here, and then polymorphic function in Haskell allow you to take the list of variable types, i.e. the function can be used on list of any types. Polymorphic function taking a list of any type as input uses the following syntax. You'll say, if I take this, that's a declaration, then I can say for this input variables I can define. So let's go to this example. Let's go to this syntax. If I have the function of type integer and then return the specific type, and then I would say if that input, if this, likely something like this, then what's the output? If that function is the same function has this type of input, the type is the same actually. This input, another version of that specific type, the output is like that. And you can repeat it multiple times you want, as you want. So the first one is defined, is named base case, the first one, and the later you can define them as different cases. So that's the definition of polymorphic. So you can take the same function, you can take with different version of the input and define the output based on that. Like I said, the first one is called the base case. So we say the polymorphic function. Okay, so I have talked about that, so I don't need to go through that. So that's an example. I would say function called length is of type t, which is list. What is inside that list? It could be t could be anything, and then that's the output. If you say if the list is empty, output is 0, but if list is something else other than the empty, then the output would be 1 plus length of x. Okay, and I can break the whole list into a and then the rest of the list. You will see that later inside that. So in Haskell we can apply class constraint to function definitions. For example, instead of saying this function is of type integer, get rid of, don't consider this part first for now. So instead of saying this function is type of a and a, we can say this function is type of numerical value of a, then we have to input value of that specific type and then one output of that specific same type. Okay, for example, in this case num is numerical values, could be integer, could be double, floating point, and etc. So for example, if I have defined something like that, then 1 plus 2 is 3. Input are type of num, integer is a valid type of num. That's okay, but this one is not okay because a is not type of num, it is a character. Okay, and then Haskell will generate for you an error. Okay, we have 4 different Haskell type classes. We have type class num, equal, order, and show. Okay, num will generate numerical values for us. Equal includes all the standard Haskell except IO and functions. So if you want to use anything other than the IO and function, you can use EQ. We have order, except function types and some other stuff, and show to show something like that. So for example, this guy is type of num. Summation. Equality is type of equality. You can say if A is equal to B, for example. Order to calculate these things like that, and show to print something like that, okay, to be able to. We will see this type later in more examples, okay. We are familiar with the definition of list from the Python. Is kind of the same, actually, I would say, in Haskell also. That's a type, that's a list of type integer. That's another list of type string. So list is a combination of multiple entries, elements, and but these elements should be the same type. They should be same type of integer, same type of string, and so on. And that's an empty list, like I said. And then you can, using the infix column in here, you can play with the list. You can say, I have a list of 1, 2, 3, 4, and empty, and so on. So they are the same, all of them. So this infix guy can help us to generate lists of different values, okay? In list, we can show the list as H and T. H is called the head. What is the head of this list is 1, and tail is called the rest apart from the head. So what is the tail of this guy? Get rid of the first one, the head, and the rest is tail, okay? We can use double sum to append two lists together. So I have this list and this list, I can append them together. And I can use this guy to select a specific element of the list. For example, if I have this list, this guy, and number 2 will give me the element of the list in position 2, not the second one, because positions are started from 0. So that means 0, 1, 2. So that means give me, please, return me, please, the value, the location 2, which is 37. Okay, so we are here. What is the last one? The last element. What is the initial part? Everything apart from the last. You had the head and tail. Head is the first, tail is the everything apart from the first. But here we have last and init. Init is everything apart from the last, and the length is the length of the string, and null is checks for you if the string is empty or not. If you say null and then the string, if it is empty, it would be true, otherwise it is false. Reverse will reverse for you the string. Take a specific location from the string for you. You can say take location 2, take the numbers of elements from the beginning. Take the first 2 elements, which would be like that. Drop will get rid of something, the last one, okay? So drops the specified number of elements from the start. When you say drop 3, that means get rid of the first 3 elements. And maximum will give you the maximum value inside. See, all of these guys are the built-in function inside the prelude, and you can use them to play with your lists inside the Haskell. For example, element test if the specified value element is contained inside the list. If I have element 4 inside the list, yes, true. Okay, and we have range. That's very interesting and something new in Haskell. You can generate a list of the specific length without using all of the elements. You can say generate a list from 1 to 5. Okay, if I use the second value inside this, I mean, what is the jump value? 1, 3, 5. Or if I say 0, 10, 50, that means 0, 10, 20 to 50. It would be applied even to characters also. That's very interesting. So A to Z, that means generate all these stuffs for me inside this guy. Can also list range with characters, for example, like that. We can generate infinite lists, something like that. 1 and go ahead, 1, 3 and go ahead, something like that. So Haskell evaluate an expression by repeatedly performing simplification. Haskell tries to simplify the things. For example, if you have this guy, it tries to simplify the thing for you. To say, okay, let's first of all, what does it mean the square? Square means multiplication of this guy by this guy. And then what does it mean? That means 3 plus 4, which is 7, and then that, something like that. And there's this multiplication and this multiplication. That's the way Haskell actually calculates the things for you. Okay, so many functions can naturally be defined in terms of other functions. For example, factorial can be defined, take an integer value and generate integer value. Factorial n can be defined as a product of all the things from 1 to 5. Okay, so I have used this product inside this one. What does it mean? It means if you give the input value n, the output would be this guy. Okay, so it calculates, like I said, try to simplifies and reduces the things for you. Production of these things, that means production of what is this thing, this guy. What does it mean, the production? Production means this guy, and then finally that's the result. Okay, we have the recursion in Haskell, which is very important. Like I said, we don't have that many cases of the iteration, so we should use recursion. For example, in factorial, if we take integer value and we want to generate the integer value, then the factorial of n is, if n is equal to 0, then the output would be 1, other 1, something like that. And that's the simplification which happens. Factorial of 3 is 3 times of factorial of 2, 3 times 2 times factorial of 1, and so on, and then we will go back slowly to get the results. Okay, the function uses a conditional expression. In Haskell, this must always have an else branch. Let's go ahead to see what has happened in here. So so far we have only seen simple function definition like square. Okay, when GHC finds an expression matching the left hand side of a definition, the evaluation mechanism replaces it by the right hand side. So for example, what is the square of 3 plus 1? Which is something like that. So that means replace the square of 3 by this guy, and then go ahead to this guy. Haskell provides more than just simple expression. In Haskell, we can go beyond this simple function implementation using the guards, patterns, and locals. These are the other tools we can use to make more mature functions. We have talked about all of these guys, the guards and the local, which we use where. What is the pattern? We have seen that already, but we will see that a little bit in detail, more detail later. Okay, so for example, we can use guard to define the function. We can say factorial function is type of integer to integer, and if it takes n, if n is equal to 0, output is 1, otherwise n is not equal to 0, output is n times factorial of n. So we see recursion, you can see guards, and so on in here. Okay, so it starts to evaluate from the first to last. It tries to go from the up to down. Okay, if none of the guards are true, then it will generate a report. It will report an error for us. That's the whole story of the guard inside the function. Okay, so that's our responsibility then, to make sure the guard always is true at some stage, otherwise an error will be generated. Okay, so in the guards we can have otherwise. We didn't have otherwise in here, but we can have otherwise in here. For example, in this case, look at that. Let's say points is type of integer to integer, and say 4 against 4 is greater than against, then the output is 3, and then at the end we have the otherwise value in here. Okay,